If you want to know how to land a rocket, you first have to understand control. It's something we take for granted, until we lose it. The real world is chaotic, it has wind, momentum and unpredictable errors. So without a human brain, how does a machine know how to steer, or exactly when to stop, before it's too late? How do we teach a mindless machine to follow a path? The answer is an incredibly elegant piece of invisible math, and to make it work, you only need exactly 3 things. For this experiment, Pond's throttle is locked. It's moving forward at a constant speed. The only thing we're allowed to control is the steering wheel. Now we need a road. A straight line is too easy to follow. Sine wave is too predictable. The real world is way more random, so we are going to use a mathematical function called Berlin noise to generate our path. It's random. We can tweak some parameters to make it look like a real path. Right now, Pond is completely off course. In control theory, this red line, the distance between where you are and where you want to be, is called the error. Our goal is simple: make the error 0. Let's give Pond his very first mathematical rule, the proportional controller. You look at the error and you react in proportion to it. If the bike is really far from the line, the error is huge, so the math tells the wheel to steer hard. As the bike gets closer to the path, the error shrinks, so the steering wheel gently relaxes. It makes perfect logical sense, and at first glance it looks like it's working. But watch what happens right here. At this exact fraction of a second, the error is 0, so the math tells the steering wheel to point perfectly straight. But there is a massive physical problem. The bike has mass, it has momentum, it's moving diagonally. By the time the algorithm realizes it has reached the target, inertia carries it right past it. Now we have a negative error, so it steers hard in the opposite direction, and it overshoots again, and so on and so on. This is the course of proportional controller. It is completely blind to momentum. It only understands the present, the exact measurement of the error right now. It doesn't know where it came from, and it has no idea where it's going. To stop the wobble and actually drive smoothly, Pond needs to be able to see the future. And to understand how machines predict the future, we have to talk about parking. Our new goal is to park the bike perfectly inside that blue box. But we have a payload. This is Baby Pond. He is riding on a custom unicycle extension, and unfortunately I forgot to program a seatbelt. Let's see what happens if we only use our proportional rule. Remember, P looks at the error, the distance to the target, and applies force. The box is far away, the error is huge, so the math screams full throttle. But P is completely blind to speed. It only knows distance, so the exact millisecond the bike reaches the box, the bike stops. But Baby Pond's momentum does not. With P, you don't realize how fast you are going until it is entirely too late. We need to add the D, the derivative. In calculus, a derivative is simply the rate of change. That's it. Instead of asking how big is the error, the derivative asks how fast is the error shrinking. The algorithm takes the error from 1 frame ago, subtracts the error right now, and divides it by time. It calculates our exact speed, but here's the genius part: we use that speed to push backwards. As Pond rockets towards the target, the proportional rule says, go forward, we aren't there yet. But the derivative rule looks at our massive speed and says, we are closing the gap way too fast. The derivative gently applies the brakes before we ever reach the target. By measuring the rate of change, the derivative predicts the future. It knows that if we don't slow down now, we will overshoot. If we apply this to our first simulation, the derivative realizes that turning too fast causes a zigzag. The present and the future are in perfect harmony. The simulation is mathematically perfect. And I say that in quotes because the real world isn't a simulation. It has friction, it has wind. What happens when a machine gets stuck, just inches away from its goal? In a perfect digital vacuum, proportional and derivative are all you need, but the real world has weather. Let's scale things up. Pond is trying to land this rocket, and now we have 3 PIDs controlling the pitch, roll and throttle. We can just run it and we can see it works fine, just like the other cases. The red arrow indicates desired path, the green arrow current tilt, and the yellow one the desired tilt. But what happens if we add upwards wind by the landing pad? The rocket tries to correct itself, but it gets stuck. It's hovering perfectly stable, but it's completely missing the target. Why? Because the arrow is now very small. The proportional force is too weak to overpower the wind. And because the rocket is hovering completely still, its speed is zero, meaning the derivative force is fast asleep. Engineers call this a steady state error. To close that final gap, the machine must look at the past, enter the I, the integral. In calculus, an integral calculates the area under a curve. In our algorithm, it acts as a memory bank. Every single second the rocket sits there, off target, the integral takes that tiny mistake and adds it to a running total. 1 second, 2 seconds, 3 seconds, the accumulated error gets massive. Eventually, the math shouts, "We have been slightly off for way too long. Override." It forces the error to be absolute zero. We finally have our holy trinity. But having the equation isn't enough. You have to tune it. Every system is different. A heavy rocket needs different math than a lightweight drone. To fix this, engineers multiply each part of our PID equation by a constant, Kp, Ki and Kd. Think of these numbers as the machine's personality. Crank the proportional constant up and you get an aggressive, hyper-responsive system that jitters and shakes. Crank the derivative constant up and you get something smooth, cautious and heavy on the brakes. Finding the perfect balance of these three numbers is an art. In the old days, engineers would tune them manually using intuition and a lot of trial and error. Today we speed up the process. We use massive computer simulations and increasingly we let neural networks and AI test millions of combinations in seconds to find the perfect balance. It's a beautiful, invisible symphony of code. Present, future and past, all working together to navigate the chaos of the real world. So yeah, that's the PID controller. Just one elegant equation keeping rockets from crashing and our world running smoothly. If you liked this video, today subscribing is the best way to support the channel. See you in the next one.